Hello, everyone. I hope you are doing well. At the beginning, I would like to thank you for listening to this recording. My name is Andrzej Wilczynski. I am from Poland, and I work as an assistant professor in the Department of Computer Science, Faculty of Computer Science and Telecommunications at Krakow University of Technology. The aim of my speech is to present a paper entitled Security Aspects in Blockchain-Based Scheduling in Mobile Multi-Cloud Computing, prepared together with Professor Kołodziej, also works at the Krakow University of Technology and in the Research and Academic Computer Network in Warsaw as well. And Dr. Jonka also works at the Krakow University of Technology. The article that will be presented has been accepted for the international workshop on secure mobile cloud computing, which takes place during the 21st International Symposium on Cluster Cloud and Internet Computing conference, which normally is held in Australia, but due to the pandemic is taking place this year online. Okay, let's start because we have only 20 minutes. First of all, I would like to say what was the motivation of our research. Recently, there has been a rapid development in mobile computing clouds and multi-clouds. The increase in popularity of such environments brings with it many challenges, including effective use of resources, ensuring an appropriate level of security, personalization of services, or supervision of over the entire environment operation. As you probably know, these problems often require new, sophisticated, and intelligent solutions. The available meta-heuristics for mapping tasks on very extensive computing resources still require improvement and in most cases do not take into account all customer requirements. Particularly ignored are aspects related to security. For instance, ensuring privacy and confidentiality of data, the possibility of falsifying the schedule by providers or its unauthorized modification by unauthorized entities. Recently, these issues are also discussed, especially in the currency market, where we are dealing with virtual currency. You have certainly heard about Bitcoin. This approach sheds completely new light of these types of problems and motivated us to improve security in the field of task scheduling in mobile cloud computing. As part of the research that we have carried out, several issues have been successfully implemented. First of all, conduct a comprehensive critical analysis of the security of our schedulers with particular emphasis on models dedicated to mobile environments and based on the blockchain technologies. Next, we developed the new model of the blockchain-based mobile multi-cloud scheduler called blockchain-based security-aware scheduling model with new security level criterion. The main concept of the blockchain-based security-aware scheduling model presented in this paper was inspired by generic model of the secure blockchain cloud scheduler defined in our previous work. And the issue of security requires special attention here. Therefore, a new task scheduling criterion called security level has been defined. The security level is influenced by three factors: p-failure, p-fake, and p-hacking, which I will describe a little later. And the last one, the developed solution, was tested using a simulator called Blockchain Secure Cloud Scheduler Simulated, implemented as part of my doctoral dissertation, which was also used to compare the proposed approach with other available task scheduling models currently available on the market. To begin with, I would like to do a brief introduction to task scheduling in mobile cloud computing and blockchain technology. First, I'm going to describe main aim of task scheduling. Multiple customers, clients may want to use the same services at the same time. So providers must properly plan tasks to achieve the desired quality and speed of services in accordance with the provisions of the SLA. Performing tasks in the correct order on available resources in such environment is very important to enable the execution of rich mobile applications on multiple mobile devices with rich user experience. And this figure presented on the slide shows a simple example of prepared schedule. The schedule is prepared for 14 tasks. There are 3 machines to execute them, and make span according to the definition for this schedule is 19 seconds, because the last task in the schedule ends here. Okay. The approach proposed in the work is based on blockchain technology, which is why a few words introducing this technology. Blockchain can be defined as a distributed ledger of records which contains transactions confirmed by the cryptographic digital signatures and are grouped in blocks. Each block usually contains a hash pointer as a link to the previous block, and a timestamp and transaction data shown in the figure on the right here. In the lower left corner, we see a blockchain network where the main actors are nodes and users. In short, the idea behind the operation of the network is that one of the nodes creates a transaction that is then propagated across the network for confirmation. Other nodes validate the transaction, and after receiving the appropriate number of confirmations of the transaction, it is placed in the block. After obtaining the appropriate number of transactions in the block is validated and attached to the chain of blocks called blockchain. Validation and adding of blocks is carried out in accordance with one of the consensus algorithms, for instance, proof of work or proof of stake. These are the most popular. As I already said, the main concept of the blockchain-based security-aware scheduling model presented on this slide was inspired by a generic model called Secure Blockchain Cloud Scheduler, defined in our previous work. And the general concept of the developed model is presented on this slide. Cloud clients and service providers are the main actors in this model. In the model, clients formulate their requirements and direct them to the cloud. These can be tasks related to the delegating the launch of resource-intensive mobile applications. Along with the specification of their needs, clients can also provide additional conditions. For example, performing tasks on a machine with special security parameters, firewall, antivirus, or processing data only on servers located in a specific geographic location. Cloud service providers collect requests from the clients, which are then forwarded to task managers. Based on the received data describing the tasks and specific customer requirements, task manager who has knowledge about the available resources, virtual machines in its cloud, select those that will be most appropriate for their execution. This selection is made taking into account safety requirements, the physical location of the machines, short waiting times for results, and for instance, small customer client budget. Then the task manager prepares a description of the selected virtual machines and tasks to be performed. And each virtual machine has 2 characteristics: computing capacity and trust level. And each task is also described by 2 characteristics: workload and security demand. In addition to machine and task specification, mainly based on customer specified security aspects, task managers also set the expected security level for the schedule. If security level is 0, all proposed schedules prepared by nodes will be accepted. Otherwise, only those with security level greater than or equal to the value given by task manager are considered. And after preparing the characteristics of tasks and machines and defining the expected security level, all information is defined as a request and placed in the request pool. here. Nodes on the blockchain select those requests for which they would like to prepare schedule. The transaction initiating node gets the request from the request pool and prepares the schedule according to its own algorithm. The obtained results along with the data from the request are placed in the transaction, which is then transmitted over the blockchain network for confirmation. And the confirming node prepares its own schedule and based on the proposed in our previous work proof of schedule algorithm decides whether to confirm it or reject. As part of this work, this algorithm was extended to include a security level before adding a transaction to the block here. The security level of the prepared schedule is calculated. If security level is at least the security level specified by task manager, the transaction is added to the block. Otherwise, it is ignored as further processing would be pointless. And the block is created and validated after collecting enough transactions. After all the requirements for building the block are met, it is added to the blockchain and distributed in the blockchain network. Adding blocks to the chain is done using the proof of stake consensus algorithm. Once the chain has been confirmed throughout the blockchain network and recognized as an official, task manager can get the schedule prepared for it from the chain and execute on his infrastructure. And this slide shows how the individual factors that make up the value of the security level criterion are calculated. P-failure is calculated based on the prepared schedule and determines the probability of machine failure during task execution due to the high security requirements specified for this task. And P-failure for a specific machine I and task J is defined in the top right corner here, taking into account the above probability of a machine failure during the execution of task J and machine I. P-failure is equal to the sum of the probabilities of failure for all tasks and divided by the number which can be seen in the formula in the upper left corner here. And the value of the next factor, P-fake, arbitrates the probability that the scheduler sent a false or incorrectly prepared schedule. In the case of single scheduling model where the schedule is not verified by other models, it can be assumed that P-fake equals 0.5. In the case of blockchain network, it is calculated according to the formula given here. NC is the number of all confirmations that the schedule is correct obtained by the node from the verification node. And NV number, this is the number of all verifications of the schedule, regardless of whether the answer was positive or negative. And the value of the last factor, p-hacking, indicates the probability of manipulation or modification of the prepared schedule by unauthorized entities. And in the case of single scheduling model, it can be assumed that p-hacking equals 0.5. In the case of blockchain scheduler, this value depends on trust factor of the attacking node. And the trust factor is the sum of workloads of tasks for all schedules added to the blockchain by attacking node within a given period of time. Given these three probabilities, the schedule security level is calculated according to the formula at the bottom of the slide. And the experiments were conducted according to the scenario presented in this slide using blockchain simulation environment, which prototype was defined in our previous work. And this simulator implements 4 different task scheduling. First of all, the scheduling process is started on 4 different scheduling models, each of them using a different algorithm, including first come, first serve, shortest job first, round robin, and hybrid heuristic method based on genetic algorithm. Then the blockchain-based security-aware scheduler is launched with 16 nodes defined in the network. Each of the nodes uses one of the 4 algorithms used by the scheduler described in point 1, and points 1 and 2 are repeated for different expected security level values. This slide shows the results of the experiments taking into account the security level value. As can be seen, the results of the experiment 1 and 2 proves that the security level of the schedule prepared by blockchain schedule is about 0.5 higher than in other cases. In experiments 3, 4, and 5, the effect of changing the size of the blockchain network and the MTC value on the value of p-fake was checked, and the MTC value is the minimum number of transaction confirmations to validate it as correct transaction. The results show that the p-fake value increases with the number of nodes in the network. The last two experiments, 6 and 7, the effect of present the effect of changing the size of the blockchain network on p hacking factor. The more transactions and blocks there are in the blockchain, the lower the p hacking value, which means that the security of the schedules increases with the length of blockchain. And the highest security level value obtained was 2.26, which is a very good result compared to the about 1.5 obtained by the other modules. Finally, a few conclusions. First of all, execution of the security mechanism usually is time consuming, which is also the main reason of high energy utilization in the cloud clusters. Such schedulers cannot be successfully implemented in mobile devices where the limited battery lifetime is the main bottleneck of completion of the security procedures and assigned tasks. The blockchain-based scheduling model presented in this paper is promising alternate methodology to the other cloud schedulers with embedded security mechanism. Second, a fully distributed blockchain system through cryptographic protocols in the consensus algorithm and local confirmation of the transactions works very well as a basic technology for the development of the secure lightweight schedulers in mobile clouds. And what about the future? The research presented in this paper is our first step towards the development of the open access blockchain-based cloud scheduling simulation environment. We plan to improve the core simulator by using the existing blockchain solutions such as Ethereum or Hyperledgers, and extended the list of the scheduling algorithm as well as improve the security mechanism. We also plan to define the realistic testbeds for testing the schedulers on the real data, which was problematic for most of the cloud schedulers with probabilistic based security models. Okay, that's it. Thank you very much again for listening to this presentation. I hope that I explained the concept adopted by us quite clearly. If you have any questions, you can contact me by email using the address provided on the first slide. Thank you again.